All right, we'll try to start above the usual construction noise. So there's a couple of straggling topics from chapter 7 that we'll start with for the first third or half of today's lecture, and then we'll move on to the next chapter, which is chapter 8. So before that, just a quick look at the exam statistics. So as I've mentioned before, this is the first time I taught the course with WebAssign. So averages compared to previous years may not be super meaningful. So we are still running a little bit below previous year's average, although that was true for the first exam as well. But again, the grading scale is easier, so that shouldn't be a cause of concern in terms of how the final grades will look. But the average was right around 51%, with a pretty large standard deviation. So there was quite a range of outcomes within that. And there was one student, congratulations, who got a perfect score in this exam. So it does happen. All right, so we're going to move on then to, as I said, finishing chapter 7. And one of the last topics we need to cover, the last one that really would involve sort of numerical problems, I would say, is another method for calculating delta H for a reaction. So we learned last time that we can use enthalpies of formation, delta H of formation, as we often call it. And if we have those values for the reactants and the products, we can sum them up on each side and then take products minus reactants, and that'll give us the delta H for the reaction using a bunch of tabulated data, not having to go through an experiment or a long sort of Hess's law puzzle to do it. The other way that we can do this is by using the bond strengths, or bond enthalpies as they're now called, to calculate delta H. So if you recall back in chapter 3, when we introduced covalent bonds, we talked about bond energy or bond strength being how strong the two atoms are bonded to each other, and some of the factors that affected that were covered at sort of a qualitative level. And so now what we're going to do is we're going to use numerical values for those bond energies to calculate delta H for a whole reaction. And this has some similarities to what we did with delta H formation, but also a couple of key differences that we will point out. So the first thing we're going to do is we're kind of imagining that the reaction takes place as such. We're going to take all the bonds on the reaction side, and we're going to break them to form all the atoms that would be present on that side of the equation. Now, this is not really how most chemical reactions happen, but that's kind of how we're formulating it in this approach, because as you recall, for a delta H, all that matters is the starting and ending points. It doesn't matter how we get there. So in this method, we're sort of assuming that every single reactant bond is going to be broken. We're going to form a bunch of atoms, and then they're going to recombine to form the products. So if we want to break all the bonds on the reactant side, that's going to require energy input. If two atoms are held together by a bond, you have to put energy into the system to break those bonds. So it requires energy. So for this step, breaking all the bonds, the delta H is going to be positive. Again, reactants means left side of the equation. That should be familiar now. We used to teach this stuff back in chapter 3, and it was kind of a mess because we hadn't covered chemical reactions or delta H at that point. But now you guys are familiar with most of the background. So that's what we're doing. We're going to take all the bond energies, bond enthalpies on the reactant side, and that's the amount of energy it's going to take to break all the bonds. And then all those atoms are going to recombine and form new bonds on the product side. And that will typically involve a different quantity of energy being released. So when you form bonds, it's exothermic. You're releasing energy as the two atoms come together and make a covalent bond. So for this step, the delta H would be negative. So in that sense, it's kind of similar to what we did with delta H formation. We're going to take all the bond energies on the reactant side, sum them together, all the bond energies on the product side, and sum them together. We're going to have two quantities that we then have to subtract. But the first key difference is that the equation that comes out of this is that instead of being products minus reactants, it's going to end up being reactants minus products. So we're going to take the sum of the bond energies, BE, as it's going to be abbreviated, of all the reactants, and we're going to subtract the bond energy on the product side. And the reason it's reactants minus products is because bond energy is defined as the amount of energy needed to break a bond is always a positive number. So again, we're going to break the bonds on the reactant side. We're going to form bonds on the product side. And that's why in this case, it's reactants minus product. It really just comes from how these terms are defined. Delta H of formation is the formation of a compound. Bond energy is defined as the breaking up of a compound. So they come from different starting points, which is why the equation gets reversed. So that's an important thing not to forget when you're doing these types of problems. There's two different ways of doing this. And again, different equations for both. As before, this Greek letter sigma means sum, so we're going to add all those up on each side. And we're using bond BE to abbreviate bond energy. Now, bond energy is sometimes called bond enthalpy or bond strength. So there's some different terms for it, but they all mean the same thing. Now, the other key difference, which will become more apparent when we do this example problem coming up next, is that in delta H of formation, every reactant or product just has a single delta H formation value you have to worry about. Because again, it's the enthalpy change associated with forming that compound from the elements. So there's one value for each compound. When we're doing it with bond energies, many compounds will have more than one bond in them, and you have to then account for each individual bond in the compound. So as a simple example, if you have H2O, oxygen bonded to two hydrogens, there's going to be two OH bonds. So it's not going to just be the bond energy of OH that you worry about, but you have to take 2 times that value. So when we're doing this, it's a little bit more intricate of a process because it's not just one value for each compound or each species. It's going to be each individual bond has to be counted up when we do this. So let's see how this works then with an example. So we're going to have this reaction here where we take this compound is called formaldehyde, which you may have heard of. We're reacting it with phosphine, which is nasty stuff. Don't play with it. And then you're going to form this new product over here. So in a problem like this, what we're going to be giving you are a whole series of bond energies. And I think the way it was set up on the homework will be you would have a table that just says all the bond energies that we have, and you have to find the right ones. But here we're just giving you the selected ones. So when you're doing this, you do have to take into account the bond order, whether it's a single, double, or a triple bond, because those all have different values for the bond energy. So if we had not given you the structure of this compound here, if we had just written it as CH2O, you would have to draw the Lewis structure to know whether it's a single, double, or triple bond between carbon and oxygen. Same with pH3. Of course, anything with hydrogen is going to be a single bond, so that one you don't really have to draw out in much detail. But in cases where there's a possibility of single, double, or triple bonds, you have to make sure you have that correct as well to get the right value that you need. Because as you'll see here in this problem, C double bond O has a bond energy of 745 kilojoules per mole. The numbers are reported per mole of bonds. That's how much energy it requires to break 1 mole of that. But if you had C single bond O, which we have in the product, that value is much different, much smaller, as it turns out, because the bond order directly relates to the bond energy. So you do need to make sure you're getting the bond order correct, because for many types of bonds, there would be multiple possible values that you have to consider and get the right one. All right, well, let's go through and then do this problem here. So it's going to take a couple of pages because this is basically an accounting exercise more than anything. So we're going to, on the reactants and product side, we're going to sum up all the bonds and the bond energies that are given. So from our first reactant here, CH2O, we have 2 CH bonds. We have to count each individual bond in this case. So there's 2 carbon-hydrogen bonds. So we're going to take the tabulated number for the CH bond and double it. So 413 kilojoules, but there's 2 of them. And then we have in this first reactant here also, we have 1 carbon-oxygen double bond. And so we have 1 mole of those bonds. The bond energy is 745 kilojoules. Getting everything today, I guess. All right. And then the second reactant is going to be pH3. We didn't draw that out, but hopefully it's obvious from the formula that it's phosphorus central atom bonded to 3 hydrogens. So there's going to be 3 phosphorus hydrogen bonds in that reactant that we have to count up as well. So we're going to take that number, multiply it by 3. The number for pH bond is 320. And so that triple becomes 960. So if we sum up all of the bond energies on the reactant side, that's going to tell us how much energy is required to break the bonds. We just add these three numbers together and get 2,531 kilojoules. Then we have to do the same thing on the product side. Yes. All right. So we can do the same thing on the product side. I'll have to flip back to it a little bit, but the product is just one thing, but it has many different bonds in it that we have to all account for. So on the product side, you have still 2 CH bonds. Now, in reality, when you're doing this, you really only have to tabulate the bonds that are changing, but sometimes it's hard to keep track of. So the sort of foolproof way of doing it is just to count every single bond on both sides and not worry about what's. So we didn't have to include the CH bonds because there's 2 CH bonds on the reaction side, 2 on the product side. Those would cancel out. But let's just do it that way so that we don't lose track of everything. So we'll do 2 CH bonds on the product as well. So that number is the same, 413 kilojoules, and there's 2 of them. But pretty much everything else on the product side is different. So we have, in this case, doesn't matter what order you do these in, but the bond between carbon and oxygen is now a single bond. So that's the value we have to use on the product side. The correct bond order is single for that one as it's drawn out. So we have 1 CO single bond with a bond energy given to us of 358 kilojoules. And that oxygen is bonded to a hydrogen, so there's 1 OH bond now. The tabulated value for the OH bond is 467. And then focusing again on carbon, there's a carbon phosphorus bond with a bond energy of 264 kilojoules. And then that phosphorus still has 2 bonds to hydrogen. So we have 3 on the reaction side. We still have 2 left on the product side. So we're going to count those. Same number, 320, but there's now 2 of them instead of 3. So we're going to double that. So a lot more numbers to keep track of on the product side, but once we have them all, we sum them together to get the sum of the bond energy on the product side of 2,555 kilojoules. All right, so then our delta H is just going to be, we have to remember this time it's reactants minus products. So on the reactant side, we got a number of 2,531 kilojoules. And then on the product side, we just figured out it's 2,555. So those two numbers subtracted from each other gives us minus 24 kilojoules. So that will be the estimated delta H for this reaction. This method is not perfect because these bond strength values that we tabulate are kind of like the average over many compounds. So it's not every CH bond is not going to be exactly 413 kilojoules. It depends on what compound it's in. It's going to vary a little bit depending on the type of compound you have. So this is an estimated value, but this is one way to do it, and it's useful in situations where you may not always know the delta H of formation of every compound you're dealing with, but if you have the individual bond strength values, which are tabulated for especially the P block, many of those covalent bonds up in the right half of the periodic table, if you have all those numbers, you can still get an estimate like we did here. It takes a little bit more time, but it still gives you a number. It's still just adding and subtracting, not too complicated mathematically. All right, any questions on that? All right, so that's the last sort of numerical topic for this chapter. The last thing that this chapter closes with, not most of the chapters in the book don't really have this, which is I'm a little bit surprised they did it for chapter 7, but a little bit of a section on the sort of, I guess you would say, the technological or societal relevance of the topics that we learn, which I'm sure is something you sometimes wonder about. I'm teaching you all these things or trying to teach you all these things, and you guys are thinking like, what's the point of this? What does it matter? Um, and that's a fair question in many cases, but it doesn't always become obvious in a general chemistry course. But here we're going to specifically talk about the relevance of all this stuff we covered in chapter 7 about energy, work, changes in energy for chemical reactions. And it's particularly relevant here in the city of Houston because where this comes into play a lot is in the energy industry. So when you're talking about fuels or the delivery of energy in other forms, this delta H is critical for all of that and a lot of the other topics that we covered as well. So let's talk about fuels a little bit first. So a fuel is a substance that has a lot of stored energy. And usually the way that we release the stored energy is by burning it. So we talked about delta H being exothermic negative for a combustion reaction in a few contexts. And so that's what a fuel is. A fuel is a substance that can be burned, and when you burn it, it releases a lot of energy because of the negative delta H. Now, there are other ways of using fuels besides burning, but burning is by far the most common. And the type of fuel that is predominant in our society over the last 100, 200 years, I would say, is fossil fuels. And so fossil fuels are those that are formed by the decomposition of living organisms over very long time periods. So they form over millions of years, and they only form under certain extreme conditions. So if you just leave out a pile of leaves for a million years, it's not going to turn into oil, but it has to be under certain temperature and pressure conditions as well. Typically deep in the ground, as we know where oil comes from. And so, as I said, most fuels that we use today are fossil fuels. And that's been true throughout the whole Industrial Revolution, still true today. So the first thing we're going to cover are what are the types of fossil fuels that we have. There's two major categories of them. Um, and the first is petroleum. So petroleum is a liquid substance and is mostly made up of hydrocarbons. So if you haven't heard that word, if you haven't heard me say that word yet, a hydrocarbon is a substance that only has carbon and hydrogen in the formula. As I said, it's a liquid. Now, when you pull petroleum out of the ground, which we at that stage we would call it crude oil, sort of black, nasty stuff that you've probably seen photos or videos of coming out of the ground, that is a sort of ghastly mixture of things. It's not just one substance. It's a lot of different hydrocarbons, a lot of different contaminants that have other elements in them. And so it needs to be processed and separated to get the things that we want out of it. So the major products of petroleum that we would use as fuels are going to be the things that we've probably heard of. So gasoline that we would put in our cars is comes from petroleum. Another type, which is diesel, jet fuel, which we use for air travel, and there's many other things that come out of petroleum as well. So the key difference between gasoline, diesel, and jet fuel, they're all hydrocarbons. It's really just the number of carbons in the formula on average. Gasoline, diesel, and jet fuel themselves are still mixtures. They're not pure substances, but they differ with respect to the average number of carbon atoms in the formula. So gasoline would have the smallest. If you see a gasoline rated as octane rating, that means it has typically around 8 carbon atoms in the formula. Diesel is a little bit higher than that, and then jet fuel would have the highest carbon content. And then besides these three major fuel products, which are often one of the biggest money makers for oil companies, a lot of chemical products come out of petroleum as well. So all the plastics that we use are derived from petroleum sources at some level. or most of the plastics we use, I should say. A lot of clothing material, a lot of building materials all come from petroleum. So there's a lot of things you can get out of there. Now, the other major type of fossil fuel is coal. It seems like here in Texas we don't use coal as much, but it still predominates in other parts of this country and around the world. So coal is a solid form mostly made up of carbon. And coal does have variable carbon content. So depending on where you get the coal from, it might have different percentages of carbon in it. There's other, as I said, minor components as well, even though it's mostly carbon. And there's a bunch of different sort of geological names for different categories of coal. I don't remember the names, like malachite, and I forget the names of them, to be honest. But and that's because we don't expect you to know the names of them. The key concept you should know if you're given a list of coal with the names associated with them, not to memorize those names, you might see them in the book, but to just understand the concept that the more carbon that's in the coal, higher the percentage of carbon, the larger amount of stored energy that it would have. Because when you burn carbon, you're primarily making CO2 as a product. And if there's more carbon in there, you're going to have more CO2 being formed, more delta H for that reaction. It'll take place to a greater extent. Versus in the other forms of coal that are lower carbon percentage, you already have some portion of it being oxidized already in the form of some carbon oxygen bonds, so you don't release as much energy when you convert that to CO2. So that's really all I want you to know about coal. There's different types. They have these fancy names that I don't remember now because I haven't looked at that chapter in a while. But the higher the percentage of carbon, the more stored energy they would have. Now, there are concerns, though, about the continued use of fossil fuels. So you've probably heard of these things in the popular media, if not in science courses, which are one of them is greenhouse gases. So a lot of the products that are released from either the production or the burning of fossil fuels are known as greenhouse gases. So these are gases that would trap heat, and then there's concerns about the extent to which they might keep the Earth's surface warm and whether that has damaging impacts on the climate. There's, of course, a lot of debate about that. This is not a climate science course, but um, that's one of the major concerns is raised about them. So methane CH4 is often a byproduct of petroleum production, and it can be used as natural gas, but a lot of times when it's extracted from petroleum, it's just burned as a waste product. So if you've seen the big oil flares going up in oil fields, that's when they're releasing gaseous hydrocarbons, primarily methane or other light hydrocarbons that would have gaseous form. It's harder to collect and store those products, so they just burn them up and release them. And that produces some amount of greenhouse gases that are known to possibly have this problem. So then, so that's a major focus then of climate science these days. To what extent do these greenhouse gases warm the planet or alter the climate in other ways? And to what extent can we mitigate that by moving away from fossil fuels? Okay. So I'm sure we're all familiar with that from things we've read and things we've seen before. Now, another concern about fossil fuels, which is not likely to be a concern in our lifetime, unless some new technology comes out that allows people to live thousands of years, but is really the long-term viability of them, because fossil fuels do have a limited supply and they won't last forever. As I said, they take millions of years to form, so we're using them most likely on a faster scale than they're going to ever be formed. We do find new sources of them from time to time, which kind of helps mitigate the concern about this, but they won't, at some level, they're not going to last forever. They take millions of years to replenish. We're going to probably use them faster than that, what we have available to us. It's always tough to estimate how much fossil fuels are available and how long will they last, because new technologies develop for extracting them that weren't available before, or we find new sources of them that we didn't know about before. The usage of fossil fuels changes over time. So those estimates are hard to go by, but it is pretty clear that at some point we're going to run out. as I said, not something that we have to immediately worry about ourselves, but it will come up in the distant future. So that has then led to a resurgence of research and development on alternative fuel sources and alternative ways of storing and generating energy that don't require fossil fuels. So one that has gotten a lot of attention is hydrogen. And there's sort of a couple of key advantages of hydrogen. So one is that its gravimetric energy density is very high. That means the amount of energy that it stores per mass. Okay, because hydrogen is the lightest compound in the world, H2. You cannot make a compound that has a smaller molar mass than that. And when you burn it, though, it releases a lot of energy. So if we take hydrogen and burn it in the presence of oxygen, it makes water is the only product, and the delta H for this reaction is quite negative, minus 286 kilojoules. So you're releasing a lot of energy by burning something that has a really light weight. So compared to gasoline or other sort of hydrocarbon sources, the amount of energy released per gram of hydrogen is very large because it's so light and it still releases a lot of energy. And alternatively, the only product of that combustion reaction is water. There's no carbon dioxide formed. Water in principle can be harvested and used, obviously, or if there's expensive or if there's inexpensive methods for taking it back, you can create sort of a closed cycle where you burn hydrogen to make water and then you recover the hydrogen from the water as a way of storing energy and using it as a fuel later down the road. So there's a lot of research going into that. Now, the downsides of hydrogen today, why don't we have hydrogen everywhere in our cars and in our homes, is that it's expensive to produce currently. And the cheapest methods to produce hydrogen still involve production of a lot of greenhouse gases. So from that standpoint, it's not really any better than, or not much better than gasoline anyway. Making hydrogen from water is very difficult and very expensive. And the other problem with hydrogen is storage and transport. To do it safely and effectively. Because unlike gasoline, hydrogen is a gas. Storing and transporting liquids is relatively safe, relatively easy to do. They're very a dense form. We'll talk about gases in chapter 8. But for gases, you have to compress them, which involves high pressures. High pressures of hydrogen are extremely explosive, so transporting them over large distances causes a lot of safety concerns. If you're familiar with the Hindenburg disaster, that was the attempt at using hydrogen to power a blimp, basically, to float a blimp, and that was a bad idea because of how explosive hydrogen is, and that was the explosion of the blimp, the Hindenburg, back in the World War II era. So there's a lot of problems with hydrogen that still haven't been fully solved. But if we could get it to work, it would be great because it's high energy density. It only produces water. You can, in principle, close this cycle. Another one that has gained a little bit of traction as well are called biofuels. So these are fuels that are generated from plant matter or produced by microorganisms. So there's all kinds of methods for genetic engineering or just for processing of plant matter that allows you to extract fuels from them, seed oils or other types of things that we'll talk about a little bit. Or you can get microorganisms to make fuels as well by re-engineering them a little bit. So those are fuels that are produced by plant matter or microorganisms. So so many of them look very similar to things that we're already using as fuels. So the advantage of biofuels is you don't have to sort of totally redesign how we're using the fuels. But the advantage is also that they're produced much faster. So unlike the natural production of petroleum, which takes millions of years, these biofuels can be produced in a typical harvest cycle. So it's just a sort of a typical annual process or even more than annual process that allows this to happen. So biofuels that are commonly available now are methanol and ethanol, which are two alcohols. These right now are not used typically as fuels by themselves, but a lot of gasoline does have, especially ethanol in it. You've probably seen that if you paid close attention to the gas pump, or things called seed oils, which are a little bit more similar to gasoline as mostly hydrocarbons that can be used in a similar way. So that's some of the future developments that are kind of becoming more and more prominent in the energy industry. So even a lot of the old school oil and gas companies that we have in Houston are starting to invest a lot of effort into alternative technologies like this, recognizing that petroleum is not going to last forever and that there's going to be regulatory and logistical challenges possibly to using it over the next coming years. So that's something that kind of relates to a lot of what we learned in this chapter. And again, not going to be a huge focus on an exam or anything, but it's something that I thought was useful to talk about a little bit. So any questions on that? All right, so we're going to move on to chapter 8 now. And so the last two chapters of this course, we're getting dangerously close to the end. We only have 2 chapters left, are going to focus on the different states of matter and some properties and things about them. So chapter 8 is all about gases, but just before we get into that, let's talk about the differences then between solid, liquid, and gas. So a solid is something that has a fixed volume and shape. So I don't know how well you can read the little molecules that are in these diagrams, but this is all just showing the different states of matter for water. So the solid form of water would be ice, and if you put a block of ice on the table, it's not going to move, it's not going to change its shape, it's going to just stay there as a block of ice. So that's how solids behave. We'll cover some things about solids in chapter 9, and then same with liquids. This is a topic we're going to talk a little bit about in chapter 9, not as much detail. The key difference with a liquid is that it still has a fixed volume. So liquid is not going to change its volume normally, but it conforms to the shape of the container. So it is able to flow. It has fluidity to it. And depending on what container you put it in, that's going to define the shape of the liquid. So if you have a tall graduated cylinder of water, it's going to occupy that shape. If you pour it into a shallow plate or a dish, it's going to spread out and occupy that shape. That's the key difference with liquids, even though the volume doesn't change in either of those situations. So that's because liquids do have an upper surface. All right, so there is a surface at the top of the liquid that confines it to whatever volume it would normally be in. Now, gases are the ones that are the most freewheeling, I suppose, because gases are substances that completely fill whatever container they're in. So they're freely flowing and they have no defined volume. They're just their volume is defined by whatever container they're in. And they have the lowest density of all 3 of these because, as we'll talk about in more detail, in order for a gas to exist, the molecules have to be really spread apart and moving around a lot. So they have pretty low density. So when we say they completely fill the container, that means if I were to release a small amount of a certain gas at the front of the room here, over some time period, it would fill the entire room. It's not going to just stay here and just hang out. It's going to fill the whole room. It's going to go everywhere. And we'll talk more about those processes later on in this chapter as well. But the first thing we have to talk about are some of the key properties of gases, how we measure them, and how they relate to each other. And so the first of those, which we saw a little bit in chapter 7, is pressure. As we described there, pressure is defined as force divided by area. So because gas molecules are constantly moving around and filling whatever container they're in, they're going to be exerting a force on the walls of those containers, and that force divided by the area is defined as pressure. So we're going to talk about 2 different ways that we would measure pressure in a laboratory setting, 2 low-tech ways, I would say. There's higher-tech ways of doing this now, of course. So the first of those is what's called a barometer. So if you're a weather nerd and you've heard of barometric pressure or seen them talk about the barometer, that's this type of device. And so the way that this one works is you typically would use a liquid like mercury, which has a really high density. You could do this with any liquid, but if you did it with water, for example, you would need a column of water that's like 3 stories tall or something. It's just not very practical to do it. So with something really dense like mercury, you would need a column that's about 1 meter tall. So if this is the bottom, it would be up to like maybe here or so. So it's not that big. And then what happens is that this device is used to measure atmospheric pressure. So that's what we use a barometer for, is to measure the pressure of whatever gas is surrounding us in the atmosphere. And that's why it's particularly relevant to weather, because as weather changes, the atmospheric pressure often changes. So those measurements can give you some insight. So the way it works is you have an empty tube or column here that's glass, and then you put that into a dish of mercury. Okay. And so the atmospheric pressure is pushing down on the surface of that mercury liquid, and it's going to force some of it up into the tube here. So it's pushing it down from the surface, and then that's going to force that up into the evacuated tube. And basically, how high that column raises is directly related to the pressure of the atmosphere around it. So if the atmosphere is pushing down harder, it's going to force more liquid into the tube, and you're going to measure a higher reading then as a result. So the atmospheric pressure is around 760 millimeters of mercury. So we abbreviate that as mmHg for millimeters of mercury. Hg is the atomic symbol for mercury. So if you're at sea level, typical day, you're going to measure a height of around 760 millimeters. And that value will vary depending on the weather conditions that day. But it's around that value, which is about roughly 2 feet tall or so, to 2.5 feet tall. But if we were to do it with water, it would be 34 feet tall that corresponds to. So that's why we use mercury or very dense liquids like mercury to measure pressure, because you don't need a lot of it. You would need a huge amount of water. And so that's how a barometer works. It measures the atmosphere around us. Barometric pressure is not terribly relevant to a chemistry course, so we'll be a little bit familiar with it. But the way that we measure pressure in a chemistry experiment is with what's called a manometer. So we use a manometer to measure the pressure of a sample of gas. So we're going to talk about today the properties of gases and how they relate to each other. And one of those is pressure, and this is how we would measure it in a laboratory setting and see how does the pressure change if we do something to the gas. So there's two types of manometers that are a little bit different from each other. They look very similar. So what you have is you have sort of a glass bulb here that you put the sample of gas into, and then it's connected to this U-shaped tube. So the U-shaped tube has some mercury in it. And if there's no gas present at all, if the pressure here is zero, you're going to, initially, the two sides are going to be equal. So this is what's called a closed-end manometer. This glass tube at the top here is completely closed off. So there's no gas pressure coming from the other side. So in the absence of anything, those two will be equal. If you introduce a gas into this bulb here, it's going to push down on this side, which is then going to cause that side to rise up because they're just connected in a U-shaped tube. So you're going to get a difference in height then between these two sides here. So in a closed-end manometer, which is shown here on the left, you're measuring the pressure relative to vacuum, or in other words, you're measuring the absolute pressure, because here there's no pressure on the other side coming from this direction. It's just the pressure of the gas pushing down this way, nothing opposing it. And so then you're going to measure a difference in height between the two sides, and that's going to be equal exactly to the pressure of the gas in millimeters of mercury. So again, that's the typical unit we're starting with, millimeters of mercury. Now the other type is an open-end manometer. So the difference here is that this side of the tube is completely open to whatever air is around you. And so what you're doing in an open-end manometer is you're measuring the pressure relative to the atmospheric pressure. So in this case, what you would have is the gas is going to be pushing on one side of the tube, the atmosphere is going to be pushing on the other. So there's going to be kind of like a battle between the two of which one's bigger. And so the pressure in this case is going to be the atmospheric pressure plus or minus the difference in height between the two sides. So in this diagram here that's shown, if the gas pressure is higher than the atmosphere, the mercury is going to be lower on that side because the gas is pushing down harder than the atmosphere is on the other side. If the atmospheric pressure is higher than the pressure of the gas, it would be the opposite. The side on the atmospheric side would end up being lower because that side is pushing down harder. So as I said, it's a competition between the two, and the gas pressure is either going to be larger or smaller than the atmospheric pressure by the value of that difference in height, depending on which side is higher or lower. So there's probably going to be some homework questions that ask you to think about that a little bit. And look at these types of diagrams and things like that. Now that we know a little bit about how it's measured, let's talk about the units for pressure, because there are a few of them we want to be familiar with. So the SI unit for pressure is called the Pascal, abbreviated as PA, named after a scientist Pascal. And because it's an SI unit, it's a compound unit of other SI units. So pressure is force divided by area. The SI unit for force is the Newton, which you've probably heard about in physics class if you've taken that. And then the SI unit for area would be square meters, meter squared. So that's what a Pascal is, where N is a Newton, which is equal to 1 kilogram meter per second squared. All right, so as we said, this is a compound unit, but all SI units. Now, the Pascal is not a very useful pressure unit in most contexts because it's a very small unit of pressure. We'll give this number in a little bit, but 1 atmospheric, so the typical pressure of the atmosphere is around 101,000 pascals. So it's a tiny unit, which means you'd have really large numbers. So we don't use it all the time, especially in chemistry. The most common one that we're going to use in a chemistry course is the atmosphere, which we already saw in chapter 7 a little bit, ATM for atmosphere. And this is defined as the average atmospheric pressure at sea level. So that's going to be sort of defined as 1 atmosphere. That's how the unit is defined. Then we would measure multiples of that to get the pressure that we're interested in. So it's the average atmospheric or barometric pressure at sea level is 1 atmosphere. And as I said, an atmosphere is much larger than a Pascal. So 1 atmosphere is 101.3 kilopascals, which is 1.013 times 10 to the 5th pascals. Now, what some people did to be a little bit clever is they said, well, 1 atmosphere is about 1 times 10 to the 5th pascal. So let's call this 1 bar. So 10 to the 5th pascal is sometimes called a bar. We're not going to see bar, I don't think, in this course, but that's another pressure unit you will sometimes see, which is almost identical to an atmosphere, but just a little bit different. And it's defined on the SI units, which the atmosphere is not. But atmosphere is going to be the one that we'll see a lot in this course. And the other one that we'll see quite a bit also is torr, because torr, which is short for Torricelli, an Italian scientist, is equal to 1 millimeter of mercury. So if we're measuring pressure with a barometer or a manometer, and we said that the column of mercury is going to rise or lower in the two depending on the pressure of the gas that's exerted on it, if we measure the height of that column in millimeters, that's going to be equal to 1 torr. So 1 torr is equal to 1 millimeter of mercury. So those two are interchangeable. So I guess torr was just special enough to get a unit named after him, but it's just a millimeter of mercury. And the key conversion factor that you're going to have to use a lot in this chapter is that 1 atmosphere is equal to 760 torr. All right, so that's the one you definitely need to know, because we will use those 2 units most often. So in 1 atmosphere, there's 760 millimeters of mercury, as we talked about, or 760 torr in those terms. All right, so that's going to be the units of pressure. So converting between them is going to be a part of what we do. So let's just do one example of that, just to remind ourselves of how this works. So this one uses some units of pressure that are not very common, that you wouldn't really have to memorize the conversions for. But if you get a compressed gas cylinder, like the type that you would use to fill helium balloons, if you've ever seen one, maybe the most recreational use, but used in a lot of industrial and scientific settings as well, those are often supplied at a pressure of 2,000 psi. So if you're in the engineering program, you'll probably see PSI, because that's a common pressure unit that's used in the United States in industry and in engineering context. It means pounds per square inch. So pound is the sort of English or English unit of force, and then square inch is our, I guess, preferred unit of area. And so it's another unit of pressure that uses English units instead of SI units. So pound per square inch. So typical compressed gas cylinder is 2,000 psi. So what would be that pressure in millimeters of mercury? Now it would be completely impractical, as we'll see, to measure a pressure of 2,000 psi using a barometer using millimeters of mercury, but we can still do the mathematical conversion just using factor label methods. So all stuff that should be a review for us at this point. We could have done this back in the review chapter. So we have 2,000 psi. Now the conversions that we're given, we don't have a direct conversion from psi to atmospheres, but we have sorry, we don't have a correct conversion from PSI to torr, but we have PSI to atmospheres is given to us, and then the familiar one that we should learn, which is atmosphere to torr. All right, so we want PSI to cancel, and we have a conversion into atmospheres from that. So 1 atmosphere is 14.7 PSI. And then we have 760 torr is 1 atmosphere. And then the trivial conversion that we could have just skipped is that 1 millimeter of mercury is 1 torr. Those two are the same. All right, so you don't have to write that one out, obviously, but mathematically it comes out to 1.03 times 10 to the 5th millimeters of mercury, which is around 100 meters of mercury. So you would need about a 10-story building filled with mercury to measure a pressure this high. So mercury barometers, mercury manometers are useful for small pressures, close to atmospheric pressure, I would say. But for measuring large pressures, obviously, they would have more sophisticated devices that don't require columns of mercury that are 300 feet tall or whatever this would be. Okay, so that's just a conversion problem, just to review how we do that. But you'll not often do these units, but again, the conversion between atmospheres and torr or millimeters of mercury is going to be very common. All right. So now we understand pressure a little bit, that because that comes up a lot in the description of gases, what we're going to build up now for the rest of today, and then we'll continue it next time by combining all of them, are relationships between the properties of gases. This is kind of interesting from a historical perspective, because these were some of the earliest chemistry experiments ever done. So when we talk about the first chemists, the first people that we would classify as chemists, these were some of the experiments that they were doing. And one of the reasons that they were doing these types of experiments is because they're not very, I guess, technically complicated. So what we're going to talk about here is going to be how the volume of a gas, how much space the gas occupies, responds to other properties of that gas. And these were easy experiments to do because measuring volume is very simple. You know, how much space does something take up? Well, how big of a container does it fill? You can do that very easily. And then you can see how that changes when other things are altered. So the first one we're going to talk about is called Boyle's Law. They're all named after people. And this is going to be the relationship between volume and pressure. So all these gas laws that we're going to build up are relationships of the volume of gas to something else, to some other property of that gas. And the first one is going to be, how does the volume of the gas and the pressure of the gas relate to each other? So we're going to watch a video that shows that a little bit. Let me turn my volume off. I think it's off, but I don't want you guys to hear this. No, don't turn off the computer. Turn the volume off.
Wait, that means we're ending your class early, right?
Yeah, I doubt it's gonna probably take them at least 20 minutes to deal with it. Probably done.
So we're done?
Yeah, we should be done. We'll be done. All right, so I'm gonna finish up this lecture all by my lonesome since we got kicked out for that fire alarm. So those of you that were in class know that. If you were watching the team's lecture and it suddenly stopped, that's why there's a fire alarm. And by the time they would have gotten that taken care of, it would have been too late to resume. So we're gonna just have a few things to finish up on my own today, and then we'll get into it more next time. So when we were interrupted, we had just finished watching a video that showed that when we reduced the pressure of something, the volume increased and vice versa. So that tells us that volume and pressure are inversely related. So we can write that as volume is inversely proportional to the pressure in this way. And that's how it sort of how we would spell it out. V is inversely proportional to P. So the little alpha symbol there means proportional to, doesn't mean equal to, it just means that they're related in that way. So as we kind of talked about when we were introducing the equation for heat, if we have two things that are proportional to each other, we can get it to an equal sign by putting a constant on one side. Now this constant is pretty useless because there is no universal constant that relates pressure and volume. But what it means we can do is we can rearrange this and write that the product of pressure and volume is constant. And it does depend on other things like the identity of the gas and the temperature and all that stuff. But because the product of pressure and volume are equal to a constant, what that means we can write is that if the pressure and volume are changing, the products of the initial pressure and volume, P1 and V1, will also equal the product of the final pressure and volume, P2, V2. So we can write this relationship then between pressure and volume that relates pressure and volume if they're changing. And so that's the statement of Boyle's law mathematically. So we can use that by itself. Now, as we'll kind of learn later on, we actually don't need all these separate equations I'm going to give you today. We can combine them all into one. But if we have this Boyle's law relationship between pressure and volume, if we have a situation where we're just talking about changes in pressure and volume, we can use those equations to figure it out. So we have, in this example problem, if we have a balloon that's inflated to a volume of 0.5 liters at sea level, and it rises to an altitude of 6.5 kilometers, and the air pressure is 0.400 atmospheres, what will the final volume be? Ignore the balloon's elasticity and assume the temperature is the same at higher altitude. All right, so what we have in this problem here is the initial volume V1 is 0.5 liters. We didn't tell you the exact pressure, but if we're at sea level, we would assume that the pressure is very close to 1 atmosphere. That's the typical atmospheric pressure at sea level. And then we said it rises where the air pressure is 0.4, so that's our P2. And then we just need to find the final volume, which we'll abbreviate here as V2. So we're going to use the Boyle's law relationship, P1 V1 equals P2 V2. And we're going to solve for the final volume, V2. So V2 is going to be equal to P1 V1 over P2, just doing a little bit of algebra to move those over. And then we just plug the numbers in. The initial pressure was 1 atmosphere. The initial volume was 0.500 liters. And the final pressure, P2, was 0.4. So we put that in the denominator here. And for problems like this, it doesn't matter what units you're using as long as you're consistent. So the two pressures need to be in the same units so that atmospheres cancels. That will give us an answer in liters for the volume. And this comes out to 1.25 liters. So the volume of the balloon would more than double in this situation. So that's mathematically how we would approach Boyle's law. As I said, we're going to have a more complete equation later on that relates everything, which would typically be our starting point. But for this one, we could do it this way since it's just pressure and volume that are changing. So the next law we're going to talk about is called Charles's law. And this is one where it's going to relate the volume to the pressure, sorry, the volume to the temperature. So the first Boyle's law was volume and pressure. This one is volume and temperature. So they all deal with the volume of the gas and how it changes with respect to other parameters. So if we can watch a video for this one as well. Thought I already still had it open. Guess I closed that out. So I'm gonna load that video up here. All right, this video has an ad in it, so just give me a second to watch the ad. It's not gonna let me go full screen. All right, so in this video here, shoot, I think my volume's still on. Let me turn it off. In this video here, they're taking a balloon that's filled with gas and they're cooling it in liquid nitrogen. So as you can see when this happens, the balloon shrivels up, telling us that the volume of the gas inside is decreasing as the temperature decreases as well. And then they pull the balloon out and they're going to let it warm back to room temperature. And you can see that as the balloon warms up, the volume restores, it gets bigger again, telling us that as the temperature increases, the volume also increases. So I don't know how to get out of here because I'm like in some weird full screen mode that I can't get out of. All right, I think we're out. Sorry about that. All right, so anyway, in that video we saw that when the gas inside the balloon cooled down, the volume decreased, and when the balloon warmed back up, the volume increased. That tells us that volume and temperature are directly proportional to each other. When the temperature goes up, the volume goes up, and vice versa. So V is directly proportional to T. So we have this proportionality. So again, we can get rid of it by putting a constant on one side. I want to put a little prime symbol here to indicate that this is not the same constant. This is not a universal constant. As we said before, it's dependent on the gas and other situations. But we can rearrange this by moving both of them to the same side and write that V1 over T1 equals V2 over T2. So when these are directly proportional, we can write this relationship between them. And that's the form of Charles's law that would be most useful to us because it gets rid of that ill-defined constant. So that's the mathematical expression of Charles's law. Now, at this point, though, in everything we're doing in Chapter 8, we have to be really careful about units for temperature. This is not a delta T. This is an absolute temperature, just T1, T2, no delta in front of it. So in this case, the units for the temperature must be in Kelvin. The only time that volume and temperature are directly related this way is when Kelvin is the units. So we haven't used Kelvin a lot yet, but the temperature in Kelvin is going to be the temperature in degrees Celsius plus 273.15. Okay. So in this part of the course, whenever we're using temperature in an equation where it's just T, it's not delta T in this case, we have to use the temperature in Kelvin. If it was delta T like we did in chapter 7, it wouldn't matter because for delta T, whether you're subtracting 2 Celsius temperatures or the 2 corresponding Kelvin temperatures, you would get the same number. But here for absolute temperature, it only works when it's in Kelvin. So this is the one time where the units are critically important. All right, so then we can do sort of the same thing as just an example problem of using this equation. So if we have a sample of gas that occupies a volume of 79.5 milliliters at 45 degrees Celsius, what volume would it occupy at 0 degrees Celsius if the pressure were held constant? So we're talking about changes in volume and temperature, so we're going to use Charles's law here, as the title tells us to, but even if we didn't realize that, volume and temperature is Charles's law, which is written in this way, as we just talked about. And then we have here, this is our initial volume, this is our initial temperature, this is our final temperature, and we're going to solve for final volume V2. Okay? So we have 3 of the things given, we just need to solve for the 4th one. Now, hopefully this helps us realize why we need Kelvin, because when we rearrange this equation to solve for V2, we would get V2 is equal to V1 times T2 over T1. And in this case, T1 is 45 degrees Celsius, T2 is 0 degrees Celsius. So if we just put the temperatures in Celsius, we would get an answer of 0 for V2. And clearly the volume doesn't go to 0 at 0 degrees Celsius. It should be non-zero. So we need to use Kelvin temperatures for this to work. So V1 can be whatever unit we want it to be. We'll just keep it in milliliters. But then for the two temperatures, we need them in Kelvin for this to work. All right, so T1 in Kelvin is 45 degrees Celsius plus, it's technically 273.15, but just adding 273 is close enough that 0.15 is not going to change anything in a material way, at least not cause you to get the problem wrong. So 318 Kelvin would be T1 in Kelvin. And then for T2, which is going to be in their denominator, it's 0 degrees Celsius. We add 273 to that, and it's going to be 273 Kelvin. So Kelvin cancels out, and that's the correct absolute temperature units. And so then we multiply those across, we get 68.2 milliliters. Okay, so Charles' law tells us that if the temperature decreases, the volume decreases. That's exactly what's happening here. We're going from 45 degrees Celsius down to 0, and our volume is shrinking from 79.5 to 68. All right, the last of the gas laws we're going to cover today is called Avogadro's law. We already had Avogadro's number earlier. It turns out that this is actually what Avogadro was known for, is this gas law. Avogadro's number was just named after him for no particular reason. But Avogadro's law deals with the relationship between the volume and the number of moles. And in this, we're going to use N as the abbreviation for number of moles. So in all the gas laws, if you see N, lowercase n, that means number of moles. Now, this one I don't have a video to show you, but I really feel like this is the easiest one for us to think about. Okay, so if we have a balloon that has 1 mole of gas in it, and we have a balloon that has 2 moles of gas in it, which one do you think would have a bigger volume? I mean, I think it's pretty obvious that the one that has 2 moles of gas would have a larger volume than a balloon that only has 1 mole of gas. That's what this little cartoon is showing here on the right. So no video to show that, but I think it's fairly obvious then that volume and number of moles are directly proportional to each other. If you have more moles of gas, they would occupy a bigger volume, all else being equal. So that's going to be the statement of Avogadro's law, that those two are directly proportional, which means we could write it as an equality with, again, a different ill-defined constant that doesn't really mean anything at this point, but then rearranging by putting both of them on the same side and setting equal to that constant, we get V1 over N1 equals V2 over N2. So this is the mathematical statement of Avogadro's law. The relationship between volume and number of moles, they are directly related to each other. All right, so that's the last of our gas laws. So those are the 4 things we need to consider. The volume of the gas, which is what we had as sort of our starting point, and then how the volume depends on pressure, temperature, and number of moles. And that gives us these 3 gas laws. So for Avogadro's law, then, if we have at a certain temperature and pressure, 28.0 grams of nitrogen occupies 20.8 liters, how much volume does 40 grams of oxygen occupy at the same temperature and pressure? So it turns out for these gas laws, they don't really depend on what gas we have. All of those relationships that we covered, Boyle's law, Charles's law, now Avogadro's law, it applies for any what's called ideal gas. We'll define later on what it means to be an ideal gas, but the identity of the gas doesn't matter. What matters is the quantities that we have. So for Avogadro's law, if we're looking for the volume change as we change the amount of gas, it's just going to be the relationship between volume and number of moles, which is V1 over N1 equals V2 over N2. So we know that we have our initial volume V1 is 20.8, and we're looking for V2 here. So we're going to solve for V2 with different amounts of gas. We don't have the number of moles directly, but we have the information to find that. So V2, which is the volume of the second sample of gas, V1 times N2 over N1. We rearrange that. And so then we just have to start plugging things in. So our initial volume was 20.8. And that's going to be the volume of the nitrogen, which is going to be N1, and then N2 is going to be the amount of oxygen. So in this equation, in this relationship that we've set up here, N1 is the number of moles of nitrogen gas that we have in the first sample that corresponds to the initial volume V1. So we have 28.0 grams of N2 and the molar mass of N2 is also 28. So this corresponds to 1 mole. So the initial volume, the initial number of moles is 1. And then the number of moles that we have for O2, which is N2 in this, the way that we've set it up here, we have 40 grams of that gas. The masses don't directly matter. What matters is the number of moles that we have. So we convert to that. 1 mole of O2 has a mass of 32 grams, as we're given here as the molar mass. So this comes out to 1.25. So we have more moles of O2 than we have of N2, so the volume will increase. So we're going to put our 1.25 moles up here. That's the amount of O2 that we have. And then when we multiply that, we get 26.0 liters, okay? So hopefully that one's not too hard to think about. We have 1.25 moles of O2, 1 mole of nitrogen. So the one that has more moles is going to occupy a larger volume, 26 instead of 20.8. But again, for these types of problems, it doesn't matter what the identity of the gas is, they're going to follow the same mathematical relationships that just depend on volume and number of moles if we're talking about Avogadro's law. All right, so that takes us to the end of what we missed today. So you'll have to sort of pick that up on your own, but it's not a bad thing to miss because at the beginning of class on Thursday, we're going to combine these 3 gas laws into one, and that's going to really be the only gas law you actually need to know, which is called the ideal gas equation that unifies all of them. So we'll get there on Thursday and do a bunch of other example problems that show what I think is the best approach to any type of problem like this that involves changes in conditions for a gas involving some combination of pressure, volume, number of moles, and temperature. All right, sorry about the interruption today. It wasn't me that pulled the fire alarm, in case you were curious about that. So hopefully that won't happen again. We'll be back in class on Thursday, sorry.